Hello. Okay. Hello, everyone, and nice to meet you all. I know it's the last presentation and everyone is exhausted. I'd like to thank the organizer for giving me this opportunity to be here today. And as I'm, I'm Anisa, and I'm from this Hungarian Wagner State Research Center of Physics. And today I'm going to present the GAN-based data station to how we can use GAN to reduce computational cost and on the behalf of Alice collaboration. So we know GAN are famous for producing realistic fake images, but here we will use to produce synthetic data. So as we saw earlier, this previous sessions, there are also use of GAN, but that was for serious image producing. So, but here, just to simplify, GAN are like machine learning frameworks that use as both comprise of two parts, like generator and discriminator. So generators learns to generate plausible data, and discriminator learns how to distinguish between the real and the produced synthetic data. And it's initially developed by Jan Goodfellow and the collaboration. And since then, there are multiple use cases also in high energy physics, but mainly the use cases are detector simulations on the digitization and also event level, especially in large hadron experiments. Uh, I mean, using GAN very, I mean, for quite a while now. And also in Alice, we also use for TPC clusterization and particle identification and some calorimeter responses. But here comes in our case, this comes to this part in the fifth part. So for machine learning training and how to use more data for machine learning classifiers and balanced data set to reduce statistical fluctuation. So as you see, there are, as I mentioned, there are like use cases for the simulations already and machine learning uses, but the bottleneck is when we have a rare particle signal and we need to produce Monte Carlo sample. And then after applying all the selection criteria and in the final state, we get very small amount of actual signal. So in that sense, we need to produce 4 or 5 times more Monte Carlo signal. So this is why it comes to this place. The reconstruction level Monte Carlo augmentations for the real signal is required, and our target is to address this analysis workflow bottleneck using GAN. So for benchmark, we use this particle called psi c. It goes to psi c to psi pi and pi in the final state. So this is also a cascade. It's also very rare. We have like thousands out of millions and millions events. So here comes our approach. As you can see here, we take the reconstructed features for this particle, and then we train GAN on the signal features and produce synthetic signal. But only produce synthetic signal is not enough. We have to make sure this produced synthetic uh, sample is actually meaningful, or it can be used for physics. So basically, GAN acts as a surrogate for reconstructed level MC here, and to increase MC statistics without full simulations. But we don't want to replace the detector simulation, or it's not a classifier itself. So it's in between these two parts. So then here is this GAN setup. So it's a very simple network of 3 layers of generators, fully connected neural networks. And for discriminator, we use 2 dense layer of neural net. And we choose 8 features of decay topology for this psi-C particle. For example, distributions of angle or decay length, or the impact parameter, these kind of distributions. And for training, so we use the processing. For example, just to keep it in the physical range, with crossing point angle, we can move to theta, and decay length, we can move to logarithmic 1, and move back to again to the original feature safe once the training is done. And it's this alternating training process, the same typical GAN. So we just use decay features here. And then here you can see once the training starts, it's very different. This is the Alice Monte Carlo, that our base Monte Carlo, and then this is the synthetic one. It's very different during beginning of training. And once after 200 epoch, you can see the stabilize, the training stabilize. And we also use some Kolmogorov loss and generative loss to constant our training. And then finally, we have some validation strategy. We compare like real versus GAN Monte Carlo feature distributions and Kolmogorov test and correlations and PDT validations and so on. I will tell one by one. And then here, first is the feature level validation. So first we want to see after the final training, how does it match or does not match with the actual Monte Carlo. So here you can see visually they are pretty well matched with the actual Alice Monte Carlo, the GAN sample. And for the signal count, around 53,000 sample. And then here to check statistically, so we does this Kolmogorov-Smirnov test. And this is the distance of this cumulative distance between these two features. And p-value is typically large, means the matching is good. For example, in some cases, it's not. So this is just an example how it works. But also this p-value, this direct uh, uh, KS distance test is also very sensitive, even for a very minor difference it can pick up. And then, but overall, you can see good agreement between GAN generated sample and Monte Carlo sample. And this is another correlation matrix. So we have Alice Monte Carlo correlation of this features, and then we have GAN generated Monte Carlo correlations, and then the difference between the two. And as you can see, it's how it pick up. It's very close. The difference is very small, and within on average within 0.05, and these are Pearson coefficient computed for all these features. And this is the residual heat map, which shows very close comparison. And it shows also this correlation looks very similar. It shows this generated sample largely the physics physical features are largely preserved. And then we have pairwise scattered plot also. So you can see this physical space between these two is very on the same phase space. So that means this is not random, these produced samples. So it's actually are this similar to this Alice Monte Carlo. To validate even more, so we use this BDT, like boost decision tree, which is normally used as a classifier, which has very good quality to distinguish between signal and background, and it has been used in analysis itself. But instead, we use signal as a GAN, Alice Monte Carlo, and background as a GAN sample. And after training, BDT training on Alice and GAN sample, we see if how these two are close enough. So as you can see, if in the ideal world, if they are close, identical, then it would have been fall on the random guess. But since, I mean, here we can see a slightly above this true positive rate. So this is about by 8 or 9%. So that means GAN able to reproduce Alice Monte Carlo distribution at the more than level of 98%. And here you can see after applying this BDT score for the test and train sample, the two distributions overlap. And as you can see, it's also overlap around 0.05. So it's the strong overlap can be seen. And then we also tried to expand our training to see, like typically if we increase the just so we need to produce for training and also model complexity. But our approach is to use add more features and using the same network and same data and Monte Carlo to see if this can hold and how much it is capable of. So then so using the same underlying statistics, so here we added 4 more features in addition to the previous 8 one. And then using the same network. And as you can see here also, it's able to mimic the Alice Monte Carlo very reasonably well, except some cases where the distribution is very different, like this particular PID one. So these are the outlier which it's not able to capture properly. But here also we did the Kolmogorov-Smirnov test, but instead of this direct distance, here we summarize using mean across all the features and maximum distance. And these are the metric for good and excellent. And as you can see, for all these case, it's below 0.06, except this one. So this just to demonstrate the scalability for this higher dimensional feature space. And so minimal architecture changes are required when expanding to higher features dimensionality. And then this brings me to this computational impact. So why we want to do this? So you see, for the full Monte Carlo production, we had, for this particular benchmark, we had to request like more than 800 million events, and it took resources for 24 days and 10,000 CPUs. These are the number of output, and but CPU efficiency is only around 70%. And when brings us to the actual analysis case, we end up uh, with only 531 signal candidates out of 800 million events. And for this particular Monte Carlo, we had 86 million events. So typically for 86 million events, we needed 800 million Monte Carlo. So with this, normally we need 4 or 5 times more data. So but GAN could be useful here because we can use this particular signal candidates, and only using this moderate CERN-SWAN configuration with this 4 CPU, it takes only a few minutes to train, and the generation takes less than a minute for this for 86 million scale synthetic samples. And so as you see, like, and the training is only one time, and one can produce arbitrary number as much we want once the training is done. And this even become more relevant if the signal become more rare. So when we have 1 in a billion particle, or even more rarer like psi-CC or multi-charm baryon, or even more rare particle, this challenge become even higher. So we need some so this become much more relevant in that case. So this GAN reconstruction levels help us to decouple this full simulation cost, and help us to like scale the MC augmentation for rare workflows. So this current scope, so this is here. We did validation for feature label augmentation, correlation preservations, and also we could expand the features, and we showed that validation that the network works, and also computational scaling studies. But finally, we also need to validate this downstream validation and full analysis chain. So this is the ongoing work. We want to apply on data and train BDT on both GAN sample and Alice sample, and compare on data and extract physics signal to see if it can be useful. And so this currently ongoing. But here current work focuses on reconstruction, this MC augmentation. So this producing this synthetic signal features. And it works. To conclude, so this GAN-based reconstruction augmentation is feasible, and it preserving the feature distribution and correlation, and also GAN architecture scales to higher dimensional features without much modifications. And this also had impact on reducing the dependence on large Monte Carlo productions, which also cost large computational cost. And it enables also for augmentation for machine learning workflows, which also needs large sample for training and testing. And this has also become more relevant for the central lead ion case, as you saw in the previous talk, that we need large number of data set, and which requires GPU uses and event samples. So that this will be relevant there as well. So we have we could extend much more features, and this application, as I mentioned, and even for Ranpur and Alice-3 applications, where we even expect much more data. And we use offline, Alice offline, online computational system and parallel computational grid. It could be integrated there. So there are strong potential for GAN-based augmentations in future of high energy physics workflows, so ready to explore. And I like to thank and acknowledge this listed funding and this Wigner Scientific Computational Laboratory for facilitating this talk. And thank you so much. Yeah.
So our last question session.
Thank you, Anisha, for this nice overview. I would have two questions which are somehow related to each other. So one of the things that once you do the either using the data directly, it typically contains kind of inner correlation, which is somehow related to the detectors and the systems. This is a kind of correlated noise, I would say. The same issue can happen if you do analysis, but you know very well that you know the Monte Carlo data generators can has also specific things which are also generate some correlations. So question number one, how to get rid of this, especially the detector correlation noise, I would say. And the other thing that how can you predict the stability or the uncertainty of the generated ones?
For the noise or the noise part, I mean, I would say particular network not to check the anomaly or efficiency computation per se, but just to uh, produce more synthetic sample to surrogate the Monte Carlo. So then we would require the similar machine learning model. Like, I mean, traditionally we use BDT to classify the signal versus background or autoencoder or other GNN network or neural network. So which particularly aim for that kind of study, but here the aim is different. So we can, of course, we can around it. Like here I used GAN plus BDT. One could use GAN plus autoencoder, GAN plus neural net. So that could be studied, of course. Yeah.
No, I mean, if you once you have a generated quickly and cheaply generated set of data, then the question is how we can trust that it is not contains some inner correlations of the either from if you have the data, the real data, the detector side, if you have the Monte Carlo from the Monte Carlo side. So that is the question. And I mean, for this, I mean, you have a very nice correlation, that's for sure, but this is all what you want to measure. The question, if you want to use this analysis for a to, as you said in the very last slide, to you had to open up any further features to look for, then how can you be sure that you really what you found it is not a correlated noise or whatever in the system? That's the question. How can you get rid of this?
So, I mean, I don't know. Here we compare. We have series of validation as I showed, and finally we will also do full scale analysis. I mean, on the analysis where we actually apply on data and extract signal to see if, I mean, we have the knowledge of how it looks like, the distributions of the mass and width of any particle. So we could compare there, so how it looks, and we also have analysis that are already there, so we can see, compare if it looks similar or not, or how much it difference. In principle, it should look similar, and if it's not, then I mean, of course, we have to see if, because here you already showed that it could produce mostly like 90%. So here you can see it's very close enough. It's not 100%, but it's above 90%. So this distribution, the samples that we produced using, I mean, it's close to this Monte Carlo.
Thank you for the talk. You briefly mentioned these rare events, and my question is how well these GANs work with these very rare events. I mean, in particle physics, we are chasing these really rare events compared to the bulk. So we have orders of magnitude differences in probability. And we already know from self-driving cars where data augmentation is being used that neural networks have trouble learning stuff that they only see 1% of the data set. So there is a large discrepancy in what we are trying to have here. And my question is, are you making some special training a method or special focus on enhancing the rare events such that the GAN can learn them? And when you are computing the statistics that you show us, are you somehow correcting for the bulk? Because we expect the bulk to be fine, but what about the tails of the distribution that are very rare? Do we have a good correlation even there? Or when you say a number that, yes, we have, I don't know, 90% goodness, it's coming from the bulk that we are basically not interested in because we already know what is happening in the bulk, but we are interested in the very rare events and if they are correctly reconstructed.
So here, because we did not reconstruct it in event by, I mean, from before the event were formed. So again, here, as you see, so these are not on the event or digitization, because how the simulation work, we produce some particles, then we feed down on a like detector phase space like Geon4, and then we also then digitize, and then there are multiple phase, but then we reconstruct, and then we finally compare with the actual data, if it's close enough to data or not. Then this is how this actual simulation works. Here, applications where people are trying to generate from the generation side, also the digitization side, like there are multiple applications in the CMS and Atlas collaboration, even in Alice. This particular case, we are taking already what is reconstructed, the shape of the feature distributions, not the event by event or digitization, hit digit or hits. So we already know the distributions, how it looks, and like these are the distributions. For example, this is the crossing point angle. So this is the distribution, and when we try again, because it takes pure noise and starts to use, and then discriminator use the input shape and to like fool the network, like, and then to learn how, and then in the end we get like similar features. So here, I mean, we don't have much rarity in this case, but can use for much more rare particle using the same concept. Like if we have some particle, like any other particle, which is probability to finding that particle 1 in a billion or multiple billion, even Higgs can be found in, like they say, a needle in a like hue. So in that case also we can, in any way we have to produce some small sample of Monte Carlo, and then we have some reconstructed features, then we can, I mean, train GAN and then produce more. So that's why I mentioned that it replace the detector simulation or not itself use as a classifier to like in between. So this particular case, that our approach is that. So just to surrogate, to have more of what we already have, but we need some baseline or some sample to like train those models.
Okay, thanks.
Yeah, and for outliers, we can like constraint the itself. Like as you see, if we have outliers in this two tail, we arrange within this peak, or we can them during the training and convert once the training is done.
Thank you very much.